Look around you. Every clock ticks forward, every calendar page turns, and yet we are bound by a single, relentless direction. Time moves forward. But what if I told you that the universe itself allows for strange possibilities? That, in principle, time travel might not be pure science fiction? Today, we are going to explore one of the most tantalizing questions physics can ask. Can we build a time machine? And when we look at the laws of nature, the answer is both fascinating and deeply challenging. The universe does not forbid time travel, but it does demand creativity, courage, and an understanding of physics that stretches the limits of human imagination. Time travel begins not with fantasy, but with a profound understanding of the nature of time itself. In our everyday experience, time seems absolute and unyielding. The seconds tick by relentlessly, and the past cannot be revisited, yet physics tells us a far stranger story. Albert Einstein's theory of relativity reveals that time is not a universal constant, but a dynamic dimension intertwined with space in what we call space-time. This means that time is flexible, capable of stretching and compressing depending on motion and gravity. In essence, time is a river that can flow at different rates for different observers. The faster you move relative to another observer, the slower your personal clock ticks compared to theirs. This is not a theoretical speculation. It has been measured repeatedly. Atomic clocks on airplanes, satellites, and high-speed particles all demonstrate that time is relative, confirming that the universe itself contains the seeds of temporal manipulation. The first step toward understanding time travel is this: by moving close to the speed of light, a person can experience time at a different rate than those who remain stationary. In the most extreme case, traveling near light speed for a few years might correspond to decades or even centuries passing for those left behind on Earth. This phenomenon, known as time dilation, is a built-in mechanism for moving forward in time. It is, in a sense, a natural form of time travel sanctioned by the laws of physics. It is not science fiction, but science fact, demonstrated by countless experiments with high energy particles and accelerators, which decay more slowly as their velocities approach light speed. The implications are profound. In principle, we could send humans on journeys that allow them to experience the future firsthand, returning to Earth to discover centuries have passed. Yet achieving near light speeds is an enormous challenge. Current technology cannot accelerate macroscopic objects, let alone humans, to such velocities. Chemical rockets, which propelled us to the moon, are utterly insufficient for relativistic travel. To reach the required speeds, we would need engines powered by nuclear fusion, antimatter, or even more exotic energy sources. Fusion, the process that powers stars, offers enormous energy density. A fusion-powered spacecraft could, in principle, provide continuous thrust over years, gradually approaching relativistic velocities. Antimatter, where matter and antimatter annihilate to release pure energy, represents an even more efficient source of propulsion. However, producing, storing, and safely using antimatter is a monumental technical challenge. The energy requirements are vast, yet within the bounds of physical law. Physics allows us to envision it. Engineering determines whether we can realize it. Gravity introduces a complementary route to time travel, one that does not require near light speeds. Massive objects warp space-time, slowing time in their vicinity. Near a neutron star or black hole, time for an observer close to the mass passes far more slowly than for a distant observer. This extreme gravitational time dilation is not theoretical conjecture. It is a prediction of general relativity confirmed through astronomical observations. A spacecraft orbiting near the event horizon of a black hole would experience hours or days while years or centuries pass for the rest of the universe. Gravity, in this sense, acts as a cosmic time machine. The trick, of course, is surviving the journey. Black holes are not merely sources of time distortion. They are intensely hostile environments, with tidal forces capable of stretching a human body and intense radiation fields. Engineering a mission that exploits gravitational time dilation requires navigating the razor's edge between theoretical possibility and lethal danger. These principles of relativity and gravity are interconnected. Time is malleable, dependent on velocity and gravitational potential. This interplay is fundamental to understanding how the universe permits a form of time travel to the future. For instance, a spacecraft could combine high velocities with strategic gravitational assists from massive celestial bodies, maximizing time dilation effects while minimizing energy expenditure. Such a mission would be a triumph not just of engineering but of the human capacity to understand and exploit the hidden geometries of the cosmos. It would require precise navigation, sophisticated propulsion systems, and careful calculation of energy budgets, all synchronized with the subtle ticking of space-time itself. Beyond the engineering challenges, the concept of moving forward in time raises profound human questions. A traveler returning from relativistic speeds would find Earth dramatically altered. Cultures, societies, and technologies would evolve potentially beyond recognition. Families and friends might have aged or passed away. Civilization itself could transform while the traveler remains relatively unchanged. Time travel to the future, while physically possible, is also an emotional and philosophical journey, forcing us to confront the impermanence of human life and the transient nature of our accomplishments. It demands not only mastery over physics, but also resilience, adaptability, and a capacity to embrace change. Moreover, the very notion of velocity-dependent time brings subtle paradoxes. Synchronized clocks, once calibrated on Earth, become desynchronized as one observer moves at high speed. Communication with the outside world becomes complex. Messages sent or received are interpreted differently depending on the relative motion of sender and receiver. This is not merely a thought experiment. It is a practical reality for satellite navigation systems, which must account for relativistic time dilation to maintain accuracy. Scaling these principles to interstellar journeys magnifies these effects enormously. A spacecraft traveling at a significant fraction of light speed will require not only extraordinary engineering, but also meticulous planning of temporal consequences. In considering time travel via velocity and gravity, we also confront the energy required for acceleration and deceleration. Continuous acceleration at fractions of a percent of light speed over years or decades demands energy resources comparable to entire planetary outputs. The spacecraft must carry or access energy sources of unprecedented magnitude, whether in the form of compact nuclear reactors, vast arrays of solar collectors, or speculative forms of exotic matter. Every design decision becomes a balance between speed, protection, and sustainability. These constraints demonstrate that physics does not forbid time travel, but it does enforce rigor, demanding solutions that are efficient, reliable, and robust. Finally, these first keynotes reveal a deeper truth. Time travel to the future is not about fantasy, but about aligning our ambitions with the fundamental rules of the universe. It is not a matter of breaking laws, but of understanding them. The cosmos is generous enough to allow a form of temporal exploration, yet it is unforgiving in its requirements. Mastery of propulsion, navigation, energy, and gravity is essential. Patience, imagination, and rigorous application of physics are required. The universe offers us the gift of the future, accessible to those who can move fast enough, think deeply enough, and endure long enough to claim it. Through these first steps, the dream of time travel begins to transform from a storybook idea into a scientific possibility, grounded in reality yet stretching the limits of human ingenuity. If the first steps of time travel take us into the future through velocity and gravity, next frontier ventures into far stranger territory, the structure of space-time itself. Wormholes, hypothetical bridges connecting distant points in the universe, emerge directly from Einstein's equations of general relativity. These are not merely science fiction constructs. Mathematically, they are perfectly valid solutions to the equations that govern space and time. A wormhole could, in theory, link one region of space-time to another, allowing instantaneous travel across both distance and time. The concept challenges our intuition because it violates the simple idea that distance must be traversed sequentially. Instead, a wormhole could provide a shortcut, a tunnel through the fabric of the cosmos, bending reality in ways that defy everyday experience. The physics of wormholes introduces both promise and paradox. While the equations allow them to exist, maintaining their stability is profoundly difficult. A natural wormhole would collapse almost instantly under the pull of gravity, making passage impossible. To hold it open, theoretical physicists propose the use of exotic matter material with negative energy density. Negative energy is not something encountered in daily life, but it is predicted by quantum mechanics. Appearing in phenomena such as the Casimir effect, where the vacuum itself produces measurable forces. Stabilizing a wormhole requires creating and controlling enough exotic matter to counteract gravitational collapse. The quantities involved are immense, possibly on the scale of entire planets or stars. While the challenge is daunting, it illustrates a remarkable point: the universe permits time travel. In principle, if we can muster the ingenuity and resources to navigate its extreme demands. Equally intriguing is the implication that wormholes could connect not just spatial locations, but different moments in time. By accelerating one mouth of the wormhole to near light speeds, or placing it in a strong gravitational field and then returning it to a stationary position, time dilation would create a temporal offset between the two ends. Step through the portal and you could emerge not just in another place, but in another era. This mechanism skirts the speed of light limitation, because locally the traveler does not move faster than light. Instead, space itself is bent, carrying the traveler forward or backward in time. It is a profound illustration of how the geometry of space-time allows for possibilities that seem fantastical yet are consistent with the known laws of physics. Quantum mechanics, the other pillar of modern physics, opens yet another avenue for temporal exploration. At the smallest scales, the universe behaves in ways that defy classical intuition. Particles exist in superpositions, occupying multiple states simultaneously, and can tunnel through barriers that seem insurmountable. Some interpretations of quantum theory suggest that all possible outcomes exist simultaneously in a multiverse of parallel realities. In such a framework, traveling to the past might not create paradoxes such as the famous Grandvar paradox. Instead, it could lead to branching timelines where actions taken by a traveler unfold in a separate, self-consistent universe. The quantum multiverse is a radical idea, but it is grounded in rigorous mathematics and offers a potential pathway for navigating the logical pitfalls of time travel. Exploring these concepts requires us to confront the limits of knowledge. Wormholes, negative energy, and quantum branching are all consistent with current physical theories, yet they remain unobserved phenomena. Theoretical physics provides a map of possibilities, but empirical validation is still pending. The challenge of time travel thus exists at the intersection of imagination and experimentation. We must trust the equations, yet remain vigilant for the universe's surprises. It is a delicate balance. The laws of physics guide us, but the practical realization of a time machine depends on technological and experimental breakthroughs that may lie decades or centuries ahead. Furthermore, the engineering challenges are as severe as the theoretical ones. Constructing a wormhole, if it is possible, would require control over energy, densities, and spatial configurations far beyond current capabilities. We would need to manipulate the very fabric of space-time with precision, maintaining stability under conditions that would crush ordinary matter. Instruments capable of detecting and measuring exotic matter must operate under extreme conditions, and any spacecraft or traveler would need protection from the immense gravitational and radiation effects near the wormhole. In short, these ideas are not just high-energy physics problems, they are exercises in extreme engineering, pushing the boundaries of what humanity can physically achieve. The potential implications of successfully manipulating space-time are staggering. A stable wormhole or a controlled time bridge would not merely allow travel, it would transform our understanding of causality, history, and our place in the universe. Communication across vast distances could become instantaneous. Observation of past events could be possible. And humanity's concept of future planning would expand into temporal scales previously unimaginable. Such possibilities force us to rethink the linear model of time, suggesting that past, present, and future might be more interconnected than everyday experience implies. The universe, in this view, is not a rigid timeline, but a flexible tapestry in which paths can be traced in multiple directions. Ethical and philosophical considerations also come sharply into focus. Traveling to the past, even if possible, raises questions about influence and responsibility. Could altering events create unforeseen consequences? Would humanity bear the moral weight of rewriting history? Quantum interpretations hint at self-consistent timelines or parallel universes as solutions, but the human dimension, psychology, culture, and ethics cannot be ignored. Time travel is as much about understanding ourselves as it is about bending the cosmos. Each potential step into the past or the future carries ramifications not only for science, but for philosophy, society, and the collective story of humanity. Finally, These keynotes highlight a broader truth: the universe permits wonders far beyond our current grasp. Wormholes and quantum temporal effects are extreme examples, yet they are consistent with the known laws of physics. They remind us that the limitations of time travel are practical and technological, not absolute. Every equation, every theoretical model opens a door to possibilities that were once confined to imagination. By understanding these principles deeply, we glimpse how the cosmos itself may allow journeys through time, and we recognize that the frontier of time travel lies not only in space, but in the persistent expansion of human ingenuity and understanding. If the exploration of wormholes and quantum mechanics offers pathways to time travel, the next crucial challenge lies in understanding causality and the paradoxes that arise when manipulating time. The universe appears to have a strict order in which causes precede effects, yet the theoretical framework of relativity and quantum mechanics allow scenarios where this order could be disrupted. One of the most famous examples is the grandfather paradox. If you traveled to the past and prevented your grandfather from meeting your grandmother, would you cease to exist? Such questions are not mere thought experiments. They force physicists to confront the consistency of the universe and the limits of what is physically permissible. Any practical time machine must reconcile these potential paradoxes with the requirement that the universe remains self-consistent, a principle that underlies much of modern physics. One proposed resolution is the Novikov self-consistency principle, which suggests that any events occurring as a result of time travel must be self-consistent. In other words, if you were to travel to the past, your actions could influence events, but not in a way that would create a logical contradiction. The universe, in this view, enforces its own consistency, preventing paradoxes from occurring. While this principle is mathematically elegant, it has profound implications for free will and determinism. A time traveler could act in the past, but only in ways that preserve the timeline that led to their journey. It is a subtle and counterintuitive concept, yet it aligns with the equations of relativity and offers a framework for thinking about temporal travel without violating causality. Quantum mechanics offers another intriguing perspective on temporal paradoxes. The concept of a multiverse suggests that every possible outcome exists in a separate, parallel universe. If a time traveler were to alter an event in the past, they might not be changing their own history, but rather creating a branch in the cosmic tree of realities. In this scenario, paradoxes are avoided because the traveler's actions unfold in a parallel timeline, leaving the original history intact. This interpretation, while speculative, is grounded in rigorous mathematics and has been explored in various quantum theories. It challenges our classical notions of singular history and forces us to consider the universe as a vast, branching structure where multiple timelines coexist simultaneously. Alongside causality and paradoxes, the technological constraints of time travel present formidable obstacles. Even if the theoretical principles allow for temporal journeys, the energy and precision required are staggering. To manipulate a wormhole or stabilize spacetime for travel, we would need access to energy densities far beyond anything currently achievable, exotic matter, negative energy, and precise control over gravitational fields would be essential. These requirements highlight a profound truth. Time travel is not merely a question of imagination. It is a question of engineering on an unprecedented scale. The universe sets the rules, and while it permits extraordinary phenomena, it does not make them easy to achieve. The energy challenge is compounded by the need for protection and stability. Time machines, particularly those that involve wormholes or near light speed travel, exist in regimes where ordinary matter would be destroyed. Radiation, tidal forces, and gravitational stresses present existential threats to both travelers and equipment. Designing a system capable of withstanding these extremes requires materials and technologies far beyond our current capabilities. Superconductors, ultra-dense alloys, and fields of negative energy must be engineered and maintained with unparalleled precision. Every failure could be catastrophic, making reliability a core requirement for temporal exploration. Beyond physics and engineering, the human dimension introduces additional layers of complexity. Traveling through time is not merely a mechanical endeavor, it is a cognitive and psychological challenge. Humans are adapted to a linear perception of time with memory, anticipation, and planning structured around a forward-moving arrow. Experiencing nonlinear time or witnessing events far in the past or future could be profoundly disorienting. Maintaining mental stability, comprehension, and decision-making ability becomes an essential part of mission design. Any successful temporal voyage must account not only for the mechanics of space-time, but for the limits of human cognition and adaptability. Ethical considerations are inseparable from the technical challenges. The possibility of influencing past events raises profound moral questions. Should one intervene in historical events, knowing the actions could ripple forward with unforeseen consequences? Even if paradoxes are avoided through self-consistency or parallel timelines, the consequences of temporal interference could be vast and unpredictable. Humanity would need to develop ethical frameworks for the responsible use of time travel, balancing curiosity and exploration with the potential for harm. In this sense, mastering the physics of time travel is inseparable from cultivating wisdom and foresight. Finally, exploring causality and technological constraints underscores a broader insight. Time travel is as much about understanding ourselves as it is about bending the cosmos. The universe permits certain forms of temporal exploration, but only if we can navigate its paradoxes, harness extraordinary energies, and respect the fragile consistency of space-time. These challenges transform time travel from a simple notion of hopping through moments into a profound enterprise that tests physics, engineering, ethics, and human imagination simultaneously. The first step is recognizing that the barriers are not impossibilities but intricate puzzles, each of which deepens our understanding of the universe and our place within it. By grappling with causality, paradoxes, energy requirements, and human factors, we begin to see time travel not as an escapist fantasy, but as a frontier that synthesizes every facet of scientific thought. The fifth and sixth keynotes reveal that moving through time demands mastery over both nature and ourselves. It is a journey that challenges intellect, tests creativity, and expands the boundaries of what we perceive as possible, inviting humanity to engage with the cosmos on the most fundamental level. As we move beyond the challenges of paradoxes, causality, and technological constraints, we enter the realm of the human and societal dimensions of time travel, which are as crucial as the physics itself. The seventh key insight is the profound human dimension. Time travel is not merely a mechanical or mathematical problem. It is an exploration of consciousness, ethics, and responsibility. Imagine standing at the threshold of the past or future, holding the power to influence events on a scale previously unimaginable. The very act of crossing temporal boundaries challenges our understanding of identity and responsibility. Every decision carries consequences not just in space, but across the timeline, rippling outward in ways that may be subtle or catastrophic. Unlike ordinary technological endeavors, where risks are localized and consequences relatively contained, time travel magnifies the stakes across generations, societies, and potentially entire civilizations. This realization forces us to confront profound ethical questions. If one could travel to the past, should one intervene? Would preventing disasters or influencing historical events be a moral imperative, or would it risk destabilizing the fabric of history? Even with theoretical safeguards like self-consistent timelines or multiverse branching, the moral weight of such actions cannot be ignored. Human ambition, curiosity, and desire to improve the world might conflict with the need for restraint. Time travel demands wisdom alongside knowledge. It is not enough to master physics. One must also cultivate judgment, foresight, and an understanding of the unpredictable consequences of intervention. In this sense, the endeavor of building a time machine becomes as much a philosophical and ethical journey as a scientific one. The psychological challenges are equally profound. Humans evolved to perceive time linearly, with memory anchoring the past and anticipation shaping the future. To navigate nonlinear time, or to witness epochs separated by centuries or millennia, the human mind must adapt to perspectives far beyond normal experience. Cognitive overload, disorientation, and temporal alienation become real risks. Maintaining clarity of thought, decision-making ability, and emotional resilience becomes paramount for anyone undertaking such voyages. These psychological considerations are not secondary, they are core components of the feasibility of time travel. Without preparing the human mind to endure temporal displacement, the most advanced machinery or theoretical breakthroughs would be of little practical use. Moving to the eighth key insight the focus shifts to the frontier of physics itself. The future of our understanding may redefine what we currently consider impossible. Our current knowledge of general relativity, quantum mechanics, and cosmology allows speculation about time travel, but it remains incomplete. The unification of quantum mechanics and gravity, the elusive theory of quantum gravity, could reveal mechanisms of temporal manipulation that are currently beyond our grasp. Higher dimensions hidden within the fabric of string theory might provide shortcuts or structures in space-time that could be harnessed for travel. A universe, vast and intricate, may contain pathways through time that we have yet to imagine. Time travel is not just an engineering challenge, it is a frontier, edge of fundamental physics where theory and imagination converge. Emerging theories suggest that manipulating space-time may require control over forces and energies that are currently speculative but physically plausible. Negative energy, exotic matter, or novel configurations of space-time could serve as the foundation for temporal bridges. Even if these technologies are decades or centuries away, the equations hint at their possibility. The laws of physics allow for ingenuity. They provide constraints, but not absolute prohibitions. Every theoretical model, from relativistic time dilation to quantum branching and wormhole dynamics, illustrates that the universe is permissive, offering pathways for exploration that demand only courage, creativity, and rigorous application of scientific principles. This frontier of physics also has profound implications for human perspective. Time travel challenges our perception of reality, encouraging us to see history, present, and future not as fixed sequences, but as malleable structures within the cosmos. The possibility that we might one day witness, influence, or traverse different points in time transforms our understanding of causality, history, and responsibility. It elevates scientific inquiry from observation to participation, from describing the universe to actively engaging with its deepest structures. The pursuit of time travel is therefore not merely a quest for novelty, but a philosophical exploration of humanity's place within the temporal fabric of the cosmos. Furthermore, the implications extend beyond individual human experience to civilization as a whole. A society capable of manipulating time must achieve unprecedented levels of coordination, foresight, and technological mastery. It would need to maintain continuity of knowledge, culture, and ethical standards over long temporal horizons. Intergenerational collaboration becomes essential as the consequences of temporal implementation would unfold over periods far exceeding a single human lifetime. Time travel is, in essence, a test of civilization's maturity, resilience, and capacity for responsibility. It is an endeavor that challenges not only our science, but our values, priorities, and vision for the future. Finally, these keynotes underscore the interconnectedness of all the challenges we have discussed: physics, engineering, ethics, psychology, and civilization itself. Time travel is not a single problem with a single solution. It is a multifaceted enterprise that tests every aspect of human ingenuity. The universe allows for extraordinary possibilities, from relativistic journeys to gravitational time dilation, from wormholes to quantum branching. Yet realizing these possibilities requires more than equations and machines. It demands wisdom, foresight, and a profound understanding of ourselves. In exploring the seventh and eighth dimensions of time travel, we see that the frontier is as much internal as it is external, as much about mastering our own limits as it is about mastering the cosmos. Time travel, in this sense, becomes the ultimate mirror, reflecting both the potential and the responsibility of human intelligence, inviting us to explore not only the universe, but the deepest capacities of our own minds and societies. In conclusion, the quest to build a time machine is far more than a journey through physics. It is a journey through the very limits of human imagination, ingenuity, and responsibility. From the relativistic effects of near-light speed travel to the mind-bending possibilities of wormholes and quantum branching, the universe allows pathways that challenge our understanding of space, time, and causality. Yet beyond the equations and engineering lies the human dimension, ethics, psychology, and civilization itself, all of which must be navigated with wisdom and foresight. Time travel is not merely about moving through the cosmos, it is about expanding the horizons of what it means to be human, to imagine, to explore, and to act responsibly across the vast tapestry of time. Thank you, dear viewers, for joining this exploration of one of the most fascinating questions in science. May your curiosity continue to push boundaries, your imagination soar beyond the ordinary, and your understanding of the universe deepen with every step you take.